In today's lesson, we are going to be looking at present value. So this is an application or kind of just a different look at compound interest, primarily because when we're looking at compound interest, in the past we've been looking at, okay, well, how much am I going to have in the future? Right? How much am I going to have after a certain time period? But sometimes that's not the question we're asking. Sometimes we know what we want to have in the future. We're saving for something, right? We're saving for college. We're saving for university. We're saving for a down payment on a house or a car. Or we're saving for some like luxury item or a computer that we want. So we know what the future amount is. What we don't know is how much do I need to put into my account or how much do I need to start with so that when I save in a given scenario, I end up with that amount that I need. And that's what we're looking at with present value. So the present value formula is very, very similar to the compound interest regular formula or the future value with two slight additions. We now have PV or the present value or P out front, and it's equal to A or the future amount or the total amount times 1 plus I, so that's the same, to the power of negative n. So the n is still the same, but the negative is different. So you want to be mindful of that. It's a negative exponent in this case. So PV, present value, how much we need now or today. Right? Those are kind of the keywords that you're looking for in the question. Again, it could just use P instead or think of it as the principal. That's the value we're looking for. A, the accumulated amount or the future amount, right, or the amount at the end of the question. That's the A value. So that's something that we'd be given. The I is the interest rate per period. We still do need a calculation for that, right? So the same calculation in the past or in the previous lesson that we used when we looked at compound interest, we're doing the same thing now. And N is the same value, number of years times the number of periods per year. The only difference in the equation, it's raised to a negative exponent. So we're still going to be looking for that compound number as well in the question because that will help us calculate the I and the N, and as well as indicate to us that it is a compound interest question. So I'm just going to look at a couple of examples just to kind of get used to entering this into a calculator, finding the values, and then plugging it into the formula. So Michelle's grandparents want to retire with $1,000 or $150,000 in the bank in 9 years from now. How much should they invest now at an interest rate of 5.75% per annum, again per year, compounded quarterly? So let's go through and kind of highlight some key information. We know how much they want to have, right? The 15 or the 150,000 in 9 years. And how much should they invest now? Right, so that is a key phrase or term because that tells us that we're looking for the present value, not the future value. We want to know how much we need to put in now. Not how much we're going to have, we already know that, but how much we're going to need now. At an interest rate of 5.75% and compounded quarterly. So we can take that key information, fill it in for the variables that we need. The A value, the future amount, is 1,500. The P value or the principal, the present value, what we need now, that we don't know. The I and the N we can calculate. We do need our compound number though, which we do get from the compound quarterly. So our compound number is 4 because it's quarterly. So that means we take the percent, 5.75%, we convert it to a decimal, 0.0575, divide that by 4, and that gives us our I value. So 0.0575 divided by 4, 0.014375. I'm going to leave the full decimals there because that is the specific rate. It does end, it does terminate. And again, it could round out my values very slightly. So I do want to try to keep the full decimal place or all the decimal places. If you find that you get a very large number with many decimal places, and you don't want to go that far, at least maybe keep 3 or 4 decimal places or actual values, right? So I wouldn't count the 0 as a decimal place, but the 1, the 4, the 3, and maybe the 7, we would round up to an 8 if you had more decimal places after the 5. So just something to be mindful of when you're doing these calculations. The n, we're looking at 9 years multiplied by 4 times a year, which gives us 36 compounding periods. So our p-value then, now we can move to our formula. Our p-value, or PV, is equal to a times 1 plus I to the power of negative n. So 150,000 times 1 plus 0.014375 to the power of negative 36. I can simplify that bracket. 1.014375 raised to the power of negative 36. Again, similar to the previous lesson, make sure that you're doing the exponent first and then multiplying, or you have to follow BEDMAS when you're going through these questions. So if you have a scientific calculator, you should be able to enter it all in at once, provided that you've entered it incorrectly. And we should get a present value of $89,731.29. So it does make sense that it is less than that final amount. It's less than that 150,000 that we want, or that Michelle's grandparents want to have, right? Because we wouldn't put in 150,000 if that's what we want to gain after 9 years. So it does make sense that we're putting in a lower amount. And again, it might seem like a lot. We have to put in almost $90,000. But again, you have to keep in mind, based on this scenario, you're putting it in there and you're not doing anything with it, and you're making then almost $60,000 for doing nothing. Right? So sometimes there is a benefit to putting a large amount into your account when you're saving, because it allows you to build more interest on that. So another scenario that you might come across is if you're trying to buy something. If you're trying to buy something, they may give you a rate that you can pay off. Like, okay, so we have the original price. Oh, but how will you pay us off? In this case, for a set of furniture, $2,500, pay that off in 2 years. So they would have calculated the amount of interest there, and then came up with that value. So we want to figure out, okay, how much do we actually need to put in, or what would be the original price without the interest added in there. So kind of going through, so finding our key values. So $2,500 payable in 2 years. The loan rate is 9.5% compounded monthly. And we want to know what's the discounted rate, or if I pay it off now. So again, that's the key thing. We're looking for now, so we're looking for a present value. The future value, so if I pay it off at the end of 2 years, it will be $2,500. The interest rate that's being used to calculate this is 9.5%. But again, we have to turn it to a decimal, 0.095, and then divide it by the compound number, which in this case, compounded monthly. So our compound number is 12. So 0.095 divided by 12. Get 0.007917. So this one is rounded. And then our end value, it's 2 years times the compounding period, which is 12. So 24 compounding periods in total over this 2-year term. Now that we know all our values, we can plug it into our equation, looking at present value, a times 1 plus I to the power of negative n. Again, remember that negative. $2,500 times 1 plus 0.007917 raised to the power of negative 24. So 1.007917 to the power of negative 24. Again, make sure when you're calculating this, you do the exponent first, or the exponent term first. If you have a scientific calculator, I'll again reiterate that you can probably do it all at once if you're confident with your calculator skills. It definitely helps if you have a calculator that allows you to see everything you're entering. The iPhones don't really do that, so I don't recommend doing that. Or what you would have to do is you would have to do one part first, do the exponent part first, and then multiply that answer by the 2,500. But in the end, we get $2,068.93. So again, it does make sense that the present value is lower than the future value, right? Because interest is being added on here. So what this is saying then, if I don't want to go in that payment plan where I take kind of a loan out, or I get a loan to pay it off over 2 years, I could pay it off right now by only spending $2,068.93. However, there's the downside to that. You do need to have that amount of money up front, right? If you're paying things off over time, you kind of get the benefit of not having to pay it all up front, but you do have that kind of the negative or the con of having to pay a little bit extra. So in this case, you're paying almost maybe like about close to $350 in interest for the benefit of paying that off over 2 years instead of right now. So again, those are kind of the pros and cons you have to weigh when kind of considering loans or paying things off over time. But again, the main thing from this lesson is just understanding the present value formula. It's basically a twist on the compound interest formula, which will allow us to calculate what the current value is, or the present value, and not what the future value is. Right? So again, same kind of formulas or same kind of variables that we need to determine in small calculations. Just remember the small changes to the actual formula that we talked about to make sure that you're doing or including those when we go through and do our calculations.